And the first thing we're going to do is learn a definition. In mathematics, we like to talk about standards so that when everybody's talking about the same thing, we know what it is, right? And historically, there was a lot of times where things didn't have standards, and then there was issues. Like when a foot was the size of the king's foot, and you had two different kings, and one was tall and one was short, and we got problems with measurements. So we had to standardize things. And it got to like very important. Like when they decided on how long a meter is, there's like the meter stick somewhere in the world that's the perfect meter that if anybody forgets, they can go back to that one and find out. Because who decided that a meter was exactly that? And why did they decide that? And what happens if someone forgets? So we have standardization, and we have that for angles too. So I'm going to start off with a game, and the game is called Angles in Standard Position, Not in Standard Position. It's a not very exciting game. But what it's going to be is I'm going to have on this side the yes, on this side no. And I'm going to draw a bunch of pictures, and we're going to figure out which one they are, and then eventually after a bunch of pictures, you have to decide how you would describe what is the rule. What is the rule for an angle in standard position? So for example, here's my first one. Oh, good. This one is in standard position. But this one is not. Whoops. They used to have a shortcut that if you group things and shook them, they stuck together, but I guess that shortcut doesn't work anymore. This one is not. So just the fact that the angle goes from left to right doesn't make it in standard position. So sometimes I try to find something that's similar between those two, but a little bit different. And what do you think? Yes or no? No, actually, it's not. How about that one? This one is yes. All right. So I've given you 4 so far. I'm going to give you another one here. What do you think? Yes or no?
No.
This one is
Yes.
a no. How about this one?
Yes.
Yes? No. Sorry. When people think they know the rule, I'm not gonna let you. How about can it end here maybe? I don't know. some no's, I got some yes. This one is actually a yes. All right. Trying to think of what I maybe haven't done yet. Oh, what about this?
No.
Okay, yeah, that is a no. Good. How about
Yes.
this one is a yes. Okay, we did 5 no's, 4 yeses. If you had to draw an angle in standard position, do you think you have enough to do the rule? You think you do? What do you think the rule is for an angle in standard position?
Must the x positive axis it can go clockwise or counterclockwise.
You can go clockwise or counterclockwise, but the important thing was
That it has to go on the x.
well, that's supposed to be an N. Looks like, wow. Angles in standard position. So, an angle in standard position must start on the positive x-axis, because here's one that started on the x-axis, but the negative side. And we're going to find out that when you go counterclockwise, like this one, this might be an angle of 135 degrees. When you go counterclockwise, 90, 180, maybe this is negative 250 degrees. This one looks like maybe negative 20 degrees. Any guesses what that, an estimate for that last one would be?
1080 maybe?
All the way around is 360, all the way around again is 720. 720 plus 180, 900. Maybe this one would be 960 degrees.
Should be 10,000.
Can keep going around and around and around. Once around would be 360 degrees. You could go around more often. Okay? You can circle question number 3 for angles in standard position. Next, we're going to look at our special triangles. Certain triangles are special, and certain triangles are special allow us to do trigonometry without our calculator. And here is our first special triangle. The 45-degree triangle. If I do this, make a right angle triangle so I can use SOHCAHTOA, and make that side 45 degrees, I'm telling you that you can do each of these without your calculator. Excuse me. Well, if I could do tan of 45 degrees, I would need to know how long the opposite side is and how long the adjacent side is. But I don't have any measurements. However, in this triangle, could you tell me what the other angle is?
45.
45. And if the other angle is 45, this makes it a special kind of triangle Not only is it a right triangle because of the 90 degrees, we have a name for these triangles when two angles are the same. Does anyone remember the name of those? Yes. Yes. Anybody in English know what they're called?
Equilateral triangles, maybe?
In English we say isosceles. And an isosceles triangle not only has two angles the same, but also two sides the same. Now, the big idea from trigonometry that you have probably forgotten, because you know the little ideas, you know SOHCAHTOA, but the reason that it's so powerful is that tangent is the opposite side over the adjacent side, and it doesn't matter how big or how small the triangle would be. If you make a 45-degree triangle and double it, and you take the opposite and divide by the adjacent, it's exactly the same as when it was small. And I think this is a really easy one to see, because if these two sides were the same, it could be 2 and 2, right? It could be 5 and 5. I'm going to pick 1 and 1. But when I do opposite over adjacent, I'm going to get 1 if it's 5 divided by 5, 2 divided by 2, 100 divided by 100. It doesn't matter how big it is. This is the power of trigonometry. Trigonometry for an angle will give you the same opposite over adjacent, opposite over hypotenuse, adjacent over hypotenuse, no matter how big that triangle is, which is super powerful. Someone realized, like, oh, if I have 30 degrees, and I take the opposite side and divide by the hypotenuse, I get a half. No matter how big or how small that triangle is, this is extremely powerful. Because now I can do math not only for little triangles, but big triangles, or if I can figure out a little triangle, I can figure out a big triangle, and I can use it to solve anything. That's why trigonometry is so powerful. If I have both of those sides as 1, how did I do this? What did I just do? A squared plus b squared equals c squared. Can you see that 1 plus 1 would be 2, and then that would be c squared, so I square root it? You now can figure out sine is opposite over hypotenuse. Sine of 45 is 1 over root 2. Are we allowed to have square roots on the bottom?
No.
Do you remember how to rationalize the denominator?
Multiply by the denominator.
Multiply both by root 2, so we would get... Does it make sense that cos is also going to be root 2 over 2? Because the adjacent over hypotenuse. So from now on, 45 degrees is going to be non-calculator questions. You're going to have to be asked, what's sine of 45? And you would have to say, I know that it's root 2 over 2. Either you're going to memorize that, or you're going to be able to redraw a triangle and figure it out. Special triangle number 2. The 30-degree, 60-degree triangle. So I make a 90 degree. I make one angle 30 degrees. And does it make sense that if they added up to 180, the other angle would be 60 degrees? Okay? This is a right triangle. The angles are all different, which means the sides are all different. We have a name for a triangle where the angles are all different and the sides are all different.
Is it scalene?
It is called a scalene. I'm impressed. This is usually the one that people forget because it's actually the name of a triangle that's not special. It's like, oh, you don't have all your two sides the same? Like everything's different. It's kind of like a whole bunch of triangles are scaling. They're like not, I'm sorry. They're not really, they don't have very many special properties. So this poor triangle is a little bit sad because it, unlike the isosceles, it's like I don't have two sides that are the same. All my sides are different. All my angles are different. And so it's walking down the street, feeling a little bit sad. And it bumps into another triangle that's exactly the same as it. Also sad. And the other triangle says, well, do you want to be friends? And so the two exactly the same triangles become friends. And something special happens. Putting those two together, what do we get?
Isosceles triangle.
Three same angles,
We get a big triangle where all the angles are,
the same, and all the sides are
and then all the sides are the same. What kind of triangle is that?
Equilateral.
It's called an equilateral. Because all the angles are 60 degrees. And if all the angles are 60 degrees, that means all the sides have to be the same. So what I'm going to do is I'm going to pick a number. The number I like to pick is 2. If I pick that's 2, then this side would be 2. And both of these would be 2, which is 1 and 1. Can you do a squared plus b squared equals c squared? Well, you have the hypotenuse down. 4 minus 1 is 3. This side here will be the square root of 3. And because we can do that without our calculator, you now can do sine of 30 degrees. Where's my 30? Right here. What's opposite over hypotenuse? It is exactly a half. Cos of 30 degrees. Adjacent over hypotenuse. The square root of 3 over 2. And tan of 30 degrees. Opposite over adjacent. 1 over root 3. Are we allowed to have a square root on the bottom?
No.
No, so we have to rationalize the denominator by multiplying top and bottom by root 3. And get root 3 over 3. But because we can do 30 degrees, we can also do 60 degrees. Sine of 60 degrees. Opposite over hypotenuse. Cos of 60 degrees. Adjacent over hypotenuse. And tan of 60 degrees. Opposite over adjacent. And from now on, these angles are fair game on non-calculator parts of your question. So either you have to have it memorized that tan of 60 degrees is root 3, or you have to be able to draw that triangle and figure it out. So I show you the triangles because with 2 triangles, you have 9 things memorized. So maybe it's easier to remember 2 triangles than it is to remember 9 things. Eventually, though, it would be really nice if you didn't have to draw the triangle, and if I said cos of 60 degrees, you'd be like, 1/2. I know that right away. That's kind of what's expected in grade 12. You know it really quick. Okay? So these are our special triangles, and with learning the special triangles, you can now do questions 5 and 6. That's the preliminary stuff. Now we're ready for question number 1. They have the definition of an angle in standard position, also at the bottom of page 427. A couple things I want to just highlight there. We call where an angle ends the terminal arm. We call things of an angle, arms, and where it ends is the terminal arm. Whoa. All right, so question number 1. The point 3, 4 is on the terminal arm of an angle in standard position. So from this, we can draw a picture. Three, 4. Here is the terminal arm. It's an angle in standard position, so it starts from the positive x-axis. So our definitions become really important here. And we want to figure out how far it is from this point to the origin. That is question A. Now, this is a trigonometry unit. A very, very important strategy in a trigonometry unit is to use a certain shape. What shape do you think you would want to use in a trigonometry unit?
Triangle.
A triangle. A circle. It's funny because grade 12 trigonometry is all about circles.
Hexagon.
Can you draw a right angle triangle? Absolutely. You go back here and look at this. I made a right angle triangle. Not only did I make a right angle triangle, but I know what 2 of these sides are. How do I know that this is 3 and this is 4?
It's from the point.
From the point. Because you went 3 over and 4 up to get to that point. So you would know that your x value is 3, your y value is 4. How could I figure out the length of my hypotenuse? A squared plus b squared equals c squared. Does anybody know the answer to this?
5.
It is 5. So the answer to part A, what is the distance from R to the origin? It is 5 units. And this is a very, very famous right angle triangle. This is the first Pythagorean triplet. We call Pythagorean triplets numbers that you can do a squared plus b squared equals c squared, and all the numbers are nice whole numbers. 3, 4, 5 is the first Pythagorean triplet. After this question, I'm going to get off topic and introduce you to a bunch of Pythagorean triplets and see if you can figure out some numbers. Okay. But first, determine the primary ratios of theta. So what they're asking for is, can you figure out sine of theta, cos of theta, and tan of theta? Well, sine is what over what? You think about SOHCAHTOA, opposite over hypotenuse. Can you see that your opposite is 4 and your hypotenuse is 5? Cos, adjacent over hypotenuse. Can you see that your adjacent is 3, your hypotenuse is 5? And tan, opposite over adjacent. Those are your 3 trig ratios. Now, to find the actual angle theta to the nearest degree, you would have to use one of those. And it doesn't matter which one you use. If I use the sine one, how would I find theta? I'd have to use sine inverse. What's the opposite of cos if I use the cos one? I'd have to use cos inverse. And what's the opposite of tan if I use the tan one? I'd have to use tan inverse. So if I use the first one, I'd go to my calculator, and I'd like everybody to try this, because some calculators, maybe you borrowed from a friend, It might be that you are not in degrees. So my calculator, I'm switching to degrees. And then I go second, sine inverse 4 divided by 5. And I get 53.13. Interestingly enough, if I did cos inverse instead of 3 divided by 5, I get the exact same answer. Or if I had done tan inverse of 4 divided by 3, all three of these would have given me the exact same answer of 53 degrees, because it does say to round to the nearest degree. I get 53 degrees. So I'm going to get you to circle question 4, 8, 9, 10, and 12. And then I'm going to get off topic, because this is exciting. The first famous Pythagorean triplet. This looks like the longer side. Is 3, 4, 5. And of course you could double that and get 6, 8, 10. And that's a Pythagorean triplet, or triplet, and get 3, 12, 15. 9 squared, 3 squared, or sorry, 9 squared, 81. 12 squared, 144. Add those together, you get 225, which is 15 squared. So any multiple of this will work. But the next one is 5, 12, and 13. And the third one I'm going to show you is 7, 24, and 25. And what I want you to do is find a pattern and tell me what's the next one that I'm going to draw, or at least something I'm going to draw on it. What do you think I'm going to draw on the next one? 9, you're right. I'm going to put a 9 here. And the one after that, I'm going to put an 11. What else do you notice?
36 and 5.
What else do you notice? Close, but not quite. If I told you one more number, do you think you could get the last one? Yes? Like,
40, 40, 40.
right? I'm gonna skip to the 13 one. Okay? I'm gonna skip to the 13 one, and I'm gonna tell you this number is 84. Could you tell me the next number? 85. Did you believe me, or am I just making this up? Let's pull out our calculator. 13 squared plus 84 squared. Those are huge numbers. And what's 85 squared? Oh, it works. What? What? Okay. What do you think goes with the 9?
40.
So you're thinking 40 and 41? You're right. You could check it. 9 squared plus 40 squared is 1,681, and 41 squared happens to be 1,681. There's patterns happening. Let's figure out the 11 one, and then I want to hear what people came up with as their patterns for figuring things out.
58.
What do you think the 11 is?
58.
Nope, not 58 and 59. But you did notice the pattern that these are one apart, right? 4, 5, 12, 13, 24. So if you find one, you find the next one. But there is a pattern to be found. Find that 11 one.
60.
60. And 61? Yes. What pattern did you find?
The bottom side goes up by 4.
4 plus 4 is...
Multiples of 4.
Hmm?
Multiples of 4.
So it went up by 8. and then 12, and then 16, and then 20, and then 24. So you could keep doing that and find the next one. But I'm going to say there is also another pattern that you can skip, because how did I do the 13 then if I didn't have the 11 and the 9? And how could I skip all the way down and find the 25 one? Whew. The 25 one happens to be 312 and 313. There's another pattern that can help you find out the numbers. And all that I used was this number. So I want you to see if you can figure out a pattern between this number and these two. That is pretty cool. It is very cool.
Oh, those are if we add the two numbers,
If we add these two numbers, you get 25.
we get the square of the other side.
That's pretty
Like
cool.
5 and 4 is 9, and 9 is square 3. And that would
49,
be,
7 squared. Now, of course, to figure out the 25 one, you'd have to know what 25 squared is. So maybe that's not in your mental math.
625.
625. And 625 divided by 2 is 312.5. So does it make sense that this would be 312 and that would be 313? Pretty cool. Now this is just one set of Pythagorean triplets. There are other sets as well. Like there's the first one, the first even numbered one. That's not a multiple. Like I could double this and get 6, 8, 10. So 6 is the smallest even number one. But a 6, 8, 10 triangle is like, buddy, that's a 3, 4, 5 just doubled. Doesn't count as something new. The first new one with an even number that's small on this side is the 8. 15, 17 one. 8 squared plus 15 squared is 17 squared, and then there's a whole other group of ones like that. So Pythagorean triplets, super fascinating. And it leads into like some history of math, like some very famous history of math. Have you heard of Fermat's last theorem? So Fermat, mathematician, long time ago, I'm going to make up a number. I'm probably off by like anywhere between 100 and 500 years. But I'm going to say 1300. Okay? Who knows? It could have been way later, way earlier. But not really important. None of us were alive. And Fermat, a mathematician, said, interesting that there are numbers that a squared plus b squared equals c squared that work out nicely. Unfortunately, there are no nice numbers for a cubed plus b cubed equals c cubed. In fact, if we do anything bigger than or equal to 3, there are no nice numbers. Unfortunately, I'm writing this in the margins of this book that I have. And he writes down, I don't have enough room to show it here, why this is true. I'll show it somewhere else. And we find this book, but we don't find this somewhere else. So now another mathematician finds this and say, was Fermat right? Or was he wrong? But we don't have his proof. So it became a puzzle. Can someone find Fermat's proof? Was he right? So then there's people that say, I don't think he was right, and they would spend their time trying to find one that proves them. That you find one answer that's wrong, and you prove Fermat wrong. But they couldn't find it. Nobody could find it.
Does 0 work?
So then people said, well, I'm going to try to prove it. I'm going to try to prove that Fermat was right. And someone said, I think I've got the proof. And someone said, no, you've made a mistake. This isn't allowed. In fact, right now, historically, we would probably say that Fermat thought he had a proof, but he actually was wrong. Because Fermat's last theorem was only proven in the last 50 to 100 years. I'm going to say 50 years.
So
It needed computers to look at it. The proof is like hundreds of pages long of computers checking out multiple different scenarios before they could say, yes, we have proven that there is no a cubed plus b cubed equals c cubed for any number, ever. In fact, no a4 plus b4 equals c4 for any number, ever. Only a squared plus b squared equals c squared works out nicely. So that's a little history. History lesson of math. Yes.
Doesn't 0 work?
0 would work, but they would say for n greater than 0 and for a, b, and c part of natural numbers. So not including 0. Whole numbers that are bigger. Because obviously 0 plus 0 plus 0 always would work. Yes. Okay. So that is a little history lesson.